Hello everyone, I'm Syed Shubha, and this is our joint work with my lab mate Joseph Masters for the machine learning course in the Department of Computer Science, Louisiana State University. So our project is titled Neural Shadows, a machine learning approach to classifying entanglement phases. So very loosely speaking, what we do here is we take noisy quantum states, compress them into a compact classical representation using the classical shadows, and then we use the standard machine learning models to decide whether those states are entangled or separable under a very tight measurement budget. Now, here is the outline of our talk. So I will start with the introduction and the motivation, why the entanglement detection is hard and why we care about the classical shadows. Then I will briefly review the background and the related work, including the Warner state, concurrence, and the classical shadow formalism. And after that, I will define the problem formalism and dataset, what exactly is the classification task, how we generate labels from the physics, and how shadows become the features. Then I will describe our ML system design. And finally, Joseph will start with the experimental setup, what model we used, how we tuned them, and then present the results and the key discussion points and wrap up with the summary, limitation, and future directions. Now, moving on, the quantum entanglement is a central resource in the quantum information. So it's something Einstein initially even struggled with. Now it's actually a very important phenomenon which is like useful in the quantum communication algorithms and metrology. But the problem is like verifying like an experimental set if it's entangled or not is actually very expensive. So the standard tool we actually have is the quantum state tomography. So let's say you have an n qubit quantum state, then the density matrix is like the 2 to the power n by 2 to the power n. So you can see it's like actually exponential, and the problem here is the number of settings and the post processing cost is like both grows exponentially with the number of qubits. So even if you have the few qubits, if you include the calibration and short noise, then it becomes quite painful in the real device. So in this project, we explore a much more resource efficient alternative based on the classical shadows. Instead of reconstruct the full state, we use the randomized Pauli measurement. We will see this later. And now, once we have the classical shadow representation, we actually turn the entanglement detection problem into a standard binary classification task. And given a feature vector here from the shadow, like can a machine learning model tell if the original state was entangled or not? This is the question. So our research question is basically if we try to be precise, it is like given any classical shadow data from a noisy two-qubit system, like how do different machine learning architecture compare in classifying entangled versus separable phases, particularly in the low data and low shot regime. So here are like two important constraints which we baked into the question. First, we only see the shadows. So we don't use the true density matrix at the interference time. Second, we deliberately work at the low resource regime, a small number of state and a small number of measurement snapshot per state, because in reality you don't have infinite number of state or it's not a stable state, and also you don't have much more ensemble, or you cannot actually take many shots. Okay, so to represent the real life scenario, we have deliberately chosen the low resource regime. And then under those constraints, we basically try to compare four families: the linear baseline, the logistic regression, a tree ensemble, the random forest, a feed-forward neural network, and the RBF kernel support vector machine operating on the same features. Now, the main thing we want to understand is the bottleneck the model class, or it is the information content of the classical shadow themselves? Now, to keep the physics control and analyzable, we work with the standard family of mixed two qubit states, the Warner state. So we actually start with the maximally Bell state. This is the 5 plus, and then we actually try to mix it with noise. And the resulted density matrix, you can actually see this is given by the rho. And now you can actually there is a term called the concurrence, which you can actually analytically calculate, and you can actually show that for p is greater than 2 by 3, the concurrence actually vanishes. So that means the entanglement if you try to measure it, so this is entangled for p less than 2 by 3, and for greater than 2 by 3 this is not, which actually lets us generate the ground truth table for our ML task without any numerical optimization. And now the second ingredient is the classical shadow formalism, which was introduced by Huang, Kuang, and Preskel. The idea is to replace the full tomography with random local measurements. For each copy of the state, we choose a random Pauli basis for each qubit. We try to measure and apply a simple inversion map to get a single shot estimator, rho t. And for a single qubit measured in a Pauli basis, the inverted estimator takes the form of rho I, rho hat I, which you can see the single qubit snapshot, and the SI here, SI cat is the measured eigenstate, and for the two qubit state we just take the tensor product and then we just average over the snapshots, which is the row average. And then the key theoretical result here is the many expectation values and even nonlinear properties of rho can be estimated with a number of measurement that scales only logarithmically in the number of observable interest, which is a huge improvement over the full tomography. This is why we are using the classical shadow tomography. Now, the background and research work. So once we have the classical shadow-based feature representation, the problem becomes purely classical. So we benchmark core families, which is the logistic regression, which basically tells us like how close entangled and separable shadows are to being linearly separable in the feature space. And then the random forest, which is an ensemble of decision trees. It can model nonlinear decision boundaries and usually work quite well with small tabular dataset. And then we have the feed-forward neural network with two hidden layers, the rectified linear unit activations, the dropout. So in principle, this is a universal function approximator, but in practice, we have to be careful about overfitting because our dataset is quite small. And finally, a support vector machine with RBF kernel. This implicitly maps the 16-dimensional feature into a high dimensional. The 16 is because 2 square into 2 square. So into a high dimensional space where we look for the maximum margin separator between the entangled and the separable state. So now, if we put all this together, then we can now formalize the problem. Like each data point in our data set is a noisy 2-qubit state row drawn from the Werner family and passed through the classical shadow pipeline. The model never sees the full density matrix. It only sees the classical feature vector. And the task is the simple binary classification. Level 1 if this is entangled, level 0 if this is separable. The main constant here is like we generate only 250 sample candidate states per trial, and we take the only 25 snapshots per classical shadow snapshot for each state. So we intentionally in a low data low short regime to emulate the realistic hardware constraint. Now to generate label, we use the analytical concurrence of the Werner state, but instead of labeling exactly at the boundary, we introduce the safety gap. So if the concurrence is essentially 0, like p rho 10 to the power minus 5, we label it as separable. And if the concurrence is at least 0.1, we label it as entanglement. Anything between, we just discard it as ambiguous. So the safety gap actually avoids feeding the borderline cases to the classifier. So now I will describe how we actually build the ML system on the top of the physics informed feature. So the three parts here is the feature pipeline from the classical shadow from the 16-dimensional vector, the model architecture we just summarized, and the training and hyperparameter tuning strategy, which is important in the low data regime. And yeah, so okay, and now I will basically it takes the 16 features as input, and then so the in the logistic regression we use the L2 regularization and the class balance weight, and this is our linear reference point, and the random forest which we tune the number of trees between 50 and 100 and the maximum depth between known and 10. This controls the bias variance of the trade-off. And the FNN we fit for neural network we which is the architecture of 64 32 1. So we use the rectified linear activation with a dropout rate of 0.4 after the first hidden layer to reduce overfitting, and the a final sigmoid output to produce a probability. The network is trained with Adam and binary cross entropy, and then the RBF SVM, which we tuned both the regularization parameter C and the kernel with uh, gamma, again with the class balance statics. So the goal is not to engineer the exotic architecture, but to test standard ML tools on this quantum specific feature space. And for each training, we follow the consistent protocol of the all models. We just perform the 80 by 20 stratified split for the dataset into the training and test set. We to preserve the entangle and separable ratio. The F1 score we report are always on the held out test set. For logistic regression, random forest, and SVM, we use the grid search CV with the 5-fold cross validation and F1 score as the selection matrix. That means we search over a small grid of hyperparameters and pick the configuration that gives the best cross validated F1 on the training data. And for the feedback neural network, we implement a manual grid search over the hidden layer size, dropout rate, and the learning rate, again with the 5-fold stratified cross validation. Once we find the best configuration, we retrain the network on the full training dataset and evaluate it on the held out dataset. So this way, our model gets roughly the same level of tuning, and we avoid comparing an overtuned neural network to totally untuned baseline.
Hello, I'm Joseph Masters, and I'll continue with the experimental setup. We implemented this in Python on Google Colab with the NVIDIA T4 GPU. The libraries we used were Qtip, which is the quantum state preparation and measurement simulation, and the rest are pretty standard libraries like NumPy, SciPy, scikit-learn, PyTorch, and Matplotlib. For our parameter regime, we went with a low resource regime of 250 candidate states for a number of samples. Our number of T snapshots was 25 joint Pauli measurements per state. And after the discarding gap, we had about 230 labeled experiments per trial. So these chosen NT combinations emulate what it would look like in a realistic, real quantum computing lab setting, as opposed to having much more data and much more refined data, which would be an ideal case, but not realistic for our case. So we wanted to keep this in a realistic budget manner. So for the Monte Carlo stability evaluation, we wanted to do this to account for variance from small data sets and possible lucky splits. So we ran 100 trials. We regenerated the data for each trial. We stratified split the data 80-20 train test, and then we trained all the models and recorded the F1 scores on the holdout test set. We reported the mean plus or minus the standard deviation of the F1 scores across these 100 trials. And for the results, for the low resource trial, we show here an example run. So in this case, we had 95 separable and 135 entangled states. The F1 scores for models are for the logistic regression 0.831. The random forest was 0.829. The neural network was 0.812, and the SVM was 0.844. So each of these models performed pretty similarly. The SVM achieved the highest F1 score of 0.844 in this specific example run. And here's a plot, once again, of this single trial, where we had about 230 states and t equals 25. We can see on the plot on the right that each 4 models all performed quite similarly. So for the Monte Carlo stability analysis, we did this again to account for sampling, measurement, and data split randomness with 100 trials. And the LR, we got the mean was 0.802 plus or minus the standard deviation of 0.049. The RF was 0.820 plus or minus 0.044. The neural net was 0.814 plus or minus 0.048. And SVM, lastly, was 0.799 plus or minus 0.053. So from these data, we can see that there is no clear winner among the 4 models we tested. Even the linear and nonlinear models are pretty comparable. So here are the results from that. We can see that each of these models lingers around 0.81 plus or minus 0.01. And with the error bars, considering those, there's a high overlap between these 4 models. And we can see that no model is significantly different than any other model. And the results from our hyperparameter tuning experiment, we used a grid search combined with a cross-validation loop. And we saw that they increased the baseline models when we added hyperparameter tuning, for example, to the logistic regression. The F1 score improved from 0.806 to 0.845. And for the neural net, it improved from 0.806 to 0.866. So we can see that the hyperparameter tuning and cross-validation can help improve our model's performance. However, these tuned scores are still bounded by the information content of the shadows, and they do not contradict the Monte Carlo results we saw earlier that all models kind of saturate near that zero point 0.8 on average F1 score. And this shows that it's more a matter of the physics and the data and measurement noise and not the models themselves. And these are the results from that. For example, we show here the logistic regression and the fully connected neural network and how the scores did improve from the initial values, and they were optimized using the hyperparameter tuning and achieved a bit better scores. However, with the hyperparameter tuning, with the standard deviations, we still did not see any significant difference between any of the four models from each other. So with that, we can move into discussion, and we have three main takeaways here. One, the classical shadows are the primary bottleneck. The 16-dimensional feature vectors capture most of the exploitable information, as increasing the model complexity only yields modest improvements. Two, the model choice is secondary to the measurements. So no single model consistently outperforms any other, as the dominant factor here is the limited dataset size and shot noise. And three, tuning helps, but doesn't break the ceiling. So if we tune the hyperparameters and we have the CV loop, it can improve the F1 scores, but they're still limited by the low N and T values. So in other words, what model we choose doesn't have a huge influence on our results, because it's all limited by our data. And once again, we chose our data to be this way. It was a bit noisy and we had low N and low T values, but we did this to be realistic to what would look like in a real lab setting. So simple classical models with classical shadows are resource sufficient for 2-qubit entanglement detection. And we also saw that complex models offer little advantage in the 2-qubit Werner case. So to summarize, we build an end-to-end classical shadow pipeline for entanglement detection in 2-qubit Werner states. We tested four models, LR, RF, FNN, and SVM, in a low resource regime of N about equaling 230 and T equals 25. All nonlinear models achieve about 0.8 F1 scores with overlapping error bars across the 100 Monte Carlo trials. The logistic regression remains surprisingly competitive within about 0.02 F1 of the best nonlinear model. The hyperparameter tuning improves the model's performances. However, once again, this performance is limited by the shadow information and the data we generated, and not by the model complexity. So to conclude, with 25 snapshots, simple classical models nearly saturate the extractable information for binary entanglement detection. And some limitations here. One, for the physical model, we restrict the attention to 2-qubit Werner states with a simple depolarizing channel. Real quantum hardware exhibits additional error sources such as readout bias, coherent control errors, and crosstalk, which are not included in this study. Because of our choices for N and T, the reconstructions are relatively easy. We did not test these in higher dimensions or more complex scenarios. Furthermore, our classification was binary, entangled versus separable, with a clean analytical label, concurrence. More complex phase diagrams were not considered. So for future work, we could expand this to larger systems and richer states to have more families of entangled states that might better probe the scaling behavior of classical shadow-based classifiers. Additionally, we can move to shadow kernels and raw shadow learning. So instead of first reconstructing p-hat or rho-hat, we could build kernel methods directly on shadow overlaps or train models on raw shadow data, comparing their performance and sample complexity to our feature-based approach. Thank you very much for listening, and here are our references.